Good morning, student. In the previous class, we have discussed about basic introduction of heat transfer, in which we have discussed what is actually heat transfer and what are different mode of heat transfer. So, in this class, we will use application of heat transfer to solve some basic heat transfer problem. This lecture is mainly focused on one-dimensional heat transfer through a plane wall. So before starting, we will discuss some basic terms like what are different coordinate system. As you all aware that we have three kind of coordinate system. One is rectangular coordinate, or we also call them Cartesian coordinate. Another one is cylindrical and spherical coordinate. So in rectangular coordinate, you have three axes x, y, and z to locate a point. For example, if you want to locate this P point, you require x, y, and z value. Similarly, for cylindrical coordinate, you require these three axes, that is r, pi, and z. Here z is this vertical coordinate, and r is radial coordinate, and theta is the theta is coordinate. Similarly, in spherical coordinate, we have r, pi, and theta. So here again the r is radial coordinate, and theta and pi are angular coordinate. The second thing is that the steady and unsteady state condition. Steady and unsteady state condition means steady state condition means there is no variation in temperature with respect to time at a particular position. So there can be variation with respect to position, but there is no change in temperature with respect to position. So as you can see in this example, you can see the inside wall temperature is maintained at 50 degrees centigrade, and outside wall temperature is maintained at 70 degrees centigrade. So see here, the outside wall temperature maintained at is 15 degrees centigrade, and in this side wall temperature maintained at centigrade at 2 p.m. And after 3 hours, that is at 5, we get same temperature 15 and 70 degrees centigrade. So there is no change in temperature with respect to time. At 2 p.m. we have temperature 15 and 7 degrees centigrade. Similarly, at 5 p.m. we have same temperature. So this is an example of steady state condition. So here you can see temperature, there is temperature gradient in the wall. It means the whole wall is not maintained at uniform. There is temperature gradient. The inside wall temperature is 15 degrees centigrade, outside wall temperature is 70 degrees centigrade, and it's changing from 15 to 7 degrees centigrade. But at any at any point in the wall, there is no temperature variation with respect to time. So this is a steady state condition, and heat will transfer through that wall, because we know for heat temperature gradient is the driving force. So here temperature is 15 and 70 degrees centigrade. So we have a total of 8 degrees centigrade temperature gradient. So due to this temperature gradient, heat will transfer through this wall. Again, heat will transfer from high temperature source to low temperature source. So this side temperature maintained at 15 degrees centigrade, and here temperature maintained at 7 degrees centigrade. So heat will transfer from high temperature source to low temperature source. So heat will transfer from left to right direction. On the other hand, in transient or unsteady state condition, the temperature is not maintained constant at a particular location or point. So as you can see in this example, At 2 p.m. temperature of inside and outside of the wall is 15 and 77 degrees centigrade respectively. But at 5 p.m. the temperature change to 12 and 5 degrees centigrade. So in that case, the temperature is changing with respect to time. So due to change in temperature with respect to time, this is a unsteady state condition. And as you know, the heat transfer rate is depends on the temperature difference between the 2 points. If the temperature changes, the heat transfer rate will also change. So at unsteady state condition, we get a variable heat transfer rate. Because the temperature is changing, so heat transfer rate will also change, because the temperature difference is the main driving force for heat transfer. The third thing is the multidimensional heat transfer. So if heat transfer only in one direction, then we call them one dimensional heat transfer. And if it transfer more than one direction, then we call them multidimensional heat transfer. So as you can see in the first diagram, the inside temperature is maintained at 80 degrees centigrade, and the other end temperature maintained at 70 degrees centigrade. So as we move along the x-axis, the temperature change from 80 degrees centigrade to 70 degrees centigrade at this point. So due to this temperature variation, heat will transfer from along the x-axis, and direction of heat transfer will be this one, because heat will transfer from high temperature source to the low temperature source. Similarly, if you can see in y direction, here temperature is 70 degrees centigrade, and at the other end the temperature is maintained at 65 degrees centigrade. So again we have temperature difference along the y axis. So due to this temperature variation along the y axis, the heat will also transfer along the y axis. Now let's see in z direction. Z direction means in vertical direction. So here you can see, as we move along the z axis, temperature is remain constant at 80 degrees centigrade. Similarly, if we take this point and we move along the z axis, the temperature is maintained at 70 degrees centigrade. And at this point, if we move along the z axis, the temperature is maintained at 65 degrees centigrade. So in conclusion, we can say there is no temperature gradient along the z direction. So and temperature is uniform throughout the z direction. So there is no temperature variation along the z direction, and temperature difference is the main driving force for heat transfer. So the heat will not transfer in z direction, and heat will transfer only in x and y direction. So this is an example of two dimensional heat transfer problem, in which heat is transferring only in x and y direction. As you can see in this example, if we have a house which is maintained at some temperature, and the outside house temperature is different. Let's say inside house is 25 degrees centigrade, and outside heat temperature is centigrade. So due to this temperature difference, heat will transfer from inside of the house to the outside of the house. And if the room temperature is maintained at 25 degrees centigrade, and environment temperature is maintained at 10 degrees centigrade, so the wall of the house will also maintained at some uniform temperature. It means there is temperature variation along the length and height of the wall, and the temperature variation will be only along the thickness of the wall. So heat will transfer from inside of the house to the outside of the wall. and there are no significant temperature variation along the height and length of the wall. So heat transfer along that direction will be negligible. So this is an example of one dimensional transfer where heat is transferring only through the thickness of the wall. Now, now, if we apply energy balance for this case, so again, if we consider we have a plain wall, and the inside of the wall is maintained at 20 degree centigrade temperature, and outside of the wall is maintained at 3 degree centigrade temperature, and there is no temperature variation along the length and height of the wall. So there is temperature variation along the thickness of the wall only. Its temperature vary from 20 degree centigrade to 3 degree centigrade, and let's say it's in x direction. So there is temperature variation along the x direction which change from 20 degree centigrade to 3 degree centigrade, and there is no temperature variation along the y and z direction. Uh, the wall is maintained temperature in outside and inside plane, and temperature variation occurs only through the thickness of the wall. So the heat will transfer only in one direction, so because only in this direction there is temperature gradient. It is a problem of one dimensional heat transfer. So if we apply energy balance in that case, no, the energy is conserved. So the rate of heat transfer into the wall minus rate of heat transfer out of the wall will be equal to rate of change of energy of the wall, or rate of energy accumulation in the wall, because energy is conserved. So if we replace this rate of heat transfer into the wall by Q in and rate of heat transfer out of the wall by Q out, and this E wall is amount of energy stored in the wall, and the rate of energy accumulation with respect to time in the wall will be denoted by dE by dt. It means energy of the wall changing with respect to time. So after putting all these value in this energy balance equation, finally get this equation. Now this special case is that if we have steady state condition, so at steady state condition the rate of accumulation of energy in the wall will be equal to 0. So this term will be equal to 0. Steady state condition, the rate of accumulation of energy will be 0. So this dE wall by dt equal to 0. So in that case, this whole quantity will be equal to 0 because the right hand side will be 0. So finally we can say this Q in will be equal to Q out. And finally we can say this Q is equal to constant. Therefore, the rate of heat transfer through the wall must be constant at steady state condition. There is one more important resistance. Now, again we have this wall in which heat is the thickness of the wall. Now, the heat is transferring through the wall through conduction. So for conduction we use Fourier law of heat conduction. So the Fourier law of heat conduction is that this Q equal to a dt by dx, that we have explained in our last class. Now if at steady state condition this Q conduction, the Q means the rate of heat transfer will be constant, and this K is thermal conductivity, which is also a property of material, and if there is no significant significant, then this k can also be assumed as constant, though the k vary with temperature. But if the temperature is not significantly changed, then the change in the value of k will be negligible, or we can assume that k is constant. Another one, this a is area of the wall through which heat is transferring. So because this is a plane wall, so this k will also be constant. So if q is constant, k is constant, a is constant, then this dt by dx will also be constant. And what is this dt by dx? So here if we plot between temperature and the thickness of the wall, then the slope of this graph will be dt by dx. If we plot between temperature and thickness, then the slope will be dt by dx. So if this dt by dx is constant, it means the slope of the graph is also constant. So if slope of the graph is constant, it means we get a straight line. So here you can see the temperature profile is a straight line. This is straight because this slope of the graph is constant. But if there is a variation in either heat transfer rate or thermal conductivity or area, then we will not get this line straight. Now moving further, so this is our equation for calculating heat transfer through conduction. Now to solve this equation, we have to integrate this equation. So finally, for integrating, we convert this equation in this form by placing this dx in left hand side and integrating from this thickness 0 to L. 0 means this point and L is this point. So integrating along the thickness of the wall, and the temperature is, here temperature is T1 and here temperature is T2. So integrating from temperature T1 to T2, finally we get this equation. So after integrating this equation, the final equation will be this one. Now if we replace this L by Ka by R wall, this R wall is called the resistance, the thermal resistance due to conduction. So this equation will reduce in this form. Here R wall is equal to L by Ka, and this R wall is called thermal resistance due to conduction. So we can also represent this problem in this form. We have two temperature T1 and T2 through which heat is transferring, and we have some resistance, this R. So this is like some problem which we have solved in electrical engineering. We have some current, and current is flowing through some resistance. So here we have some temperature difference through which heat is transferring, and this one is the resistance offered by the wall. Now in the previous example, we have considered we have a wall through which heat is transferring. So now extending this problem, once heat is transferred along the wall, after that heat will further transfer to the environment. So the heat will further transfer to the environment through convection, because outside the wall we have some air, so heat has to dissipate to through environment through that air. And as I told you earlier, when there is actual movement of the fluid, the heat will transfer through convection. So here we have air, so heat will transfer through movement of the air. So this will be a convective mode of heat transfer. So for convection, as I told you earlier, we use Newton law of cooling, means this one. this Newton law of cooling. This Q equal to HA delta T. This Q is heat transfer rate, H is the heat transfer coefficient, A is effective area through which heat is transferring, and this Ts and T infinity are temperature of high temperature source point to the temperature of low temperature destination through which heat where heat is transferring. So again, if we rearrange that equation, we can write this equation in this form. Here this R convection is equal to 1 upon HA. So this R convection is called thermal resistance due to convection, or simply we can call them convection resistance, this equation. Again, we can also represent this convection heat transfer by this form. We have some temperature difference and we have some resistance through which heat is transferring. Third one is radiation heat transfer. So if the heat transfer coefficient have very less value, if H, the heat transfer coefficient, is very low, it means heat transfer through convection will be very low, because the heat transfer is directly proportional to heat transfer coefficient, and if its value is very small, then we get very low amount of heat transfer through convection. So in that case, the radiation will also play an important role, because heat will also transfer through radiation, and if this mode is not significant, then this is, will also show some significance. So if we have heat transfer through radiation, then we have to account that factor also. And the radiation heat transfer can be explained with the help of Stefan Boltzmann law, that is Q radiation will be equal to sigma epsilon sigma A Ts raised to power 4 minus T surrounding power 4. Here epsilon is emissivity of the material through which heat is transferring. This sigma is Stefan Boltzmann constant, which has value of 5.67 into 10 to the power minus 8. This Ts raised to power 4 is the surface temperature, means temperature of the wall, and T surrounding raised to power 4. This T surrounding is temperature of the environment through which heat through where heat is transferring. So if we write this equation in equivalent form of convective heat transfer, then this equation can be written as H radiation As Ts minus T surrounding. This H radiation is equivalent form of heat transfer coefficient of radiation heat transfer. So if we write this equation in equivalent form of this equation, then finally we get this equation, and after rearranging this equation, we get the here the R radiation will be equal to 1 upon H radiation As. So again, if you can see in this diagram, the heat is transferring through radiation. So here we have some inlet temperature, here we have outlet temperature through which we have radiative heat transfer resistance, and through which heat is transferring. So now in that case, the heat is transferring through both convection and radiation. So here the heat is transferring through convection, and similarly here heat is transferring from radiation. So the total amount of heat transfer through that wall will be equal to the summation of heat transfer through convection and radiation. So this Q total will be equal to Q convection plus Q radiation. So this is end of today class. If you have any question or doubt, you can write in the comment box. Thank you very much.